Okay, so yeah, we were discussing differential forms. On Riemann surfaces. Okay. So as a prototype of this situation, we took an open subset of C to start with. You see, so this is open. And so because an open subset of C is a real manifold also, and for real manifolds, I define the Rom complex, right? So let me recall this the Rom complex of U. Right? So what was that? That was just a complex of this form, omega 0 of U, omega 1 of U, and then omega 2 of U. It goes to 0 here, and here comes to 0. So there is this wrong differential B, right? So we had, if you recall, we had omega 0 of U. By the way, as I said, sometimes people are careful enough to put C here. So it means that everything we take is complex valued. So omega 0 of U or C of U is just C infinity C of U. This is a space of the smooth complex valued functions on U, right? Smooth complex valued functions on U. And then omega 1 C of U. So these are just the smooth functions, as you remember. And omega 1 C of U, this is just smooth one forms, a complex valued one forms. This is the set of all f dx plus g dy, where f and g belongs to omega 0, belongs to C infinity C of U. So these are smooth one forms. Right? And omega 2 C of U is the set of all expressions of the following form, f dx wedge dy. Sometimes you may even drop this wedge sign, just say dx dy. So where f again belongs to C infinity C of U, these are smooth two forms. And there's nothing else. Now this D we defined at this level. So D is the Rom differential. So D of F, you said is df partial F partial X dx plus partial F partial Y dy. And we have to define D of one form, F dx plus G dy. So the recipe was very general, was that this is equal to df wedge dx, right, plus dg wedge dy. Remember, I said that to differentiate a form, we just differentiate the coefficients, because the coefficients are just functions, and we can differentiate functions by using the Rom, and then wedge it with the rest. So if you go through this now, this definition using the first step, then you can write this in terms of dx wedge dy, right? So this turns out this is equal to, so this is partial f with respect to x dx, which is wedge dx is 0, and then with respect to dy becomes dy wedge dx, but that's minus dx wedge dy. So this first term is minus df dy There is dx by dy here. And this term gives you dg dx dx wedge dy. The other one is 0 plus dg dg dx. Sorry. Yes. Yes. So you get this. This is minus, of course. Okay. So this is the differential or the wrong derivative or the wrong differential of a one form. And of course, these expressions you have seen in vector analysis. I mean, in vector analysis, we don't talk about differential forms. We always talk about vector fields, but they are vector field. They are differential forms in disguise. Yeah, because vector fields are easier to figure out rather than a differential form, which is a dual object more or less. Anyhow, this is like the expression for the curve, part of the component for the curve of the vector field, but that's okay. Okay, so this is these things, and then we define the wrong cohomology as well. Cohomology, which is the of course, I mean, d squared is equal to 0, right? That gives you the cohomology of this complex. So we have three groups: H0, H1, and HT, right? So there is H0 the wrong of U, H1 the wrong of U, and H2 the wrong of U. And I told you that by some big theorem of actually Riemann himself, this turns out to be given by to be also giving the simplicial or the singular homology of the space. Okay, but we don't need that much yet. But this is something that is very general, works for all smooth manifolds, and works in all dimensions. That's very, very general. So now, but the point is, so what happens in the complex case? So because your space now is complex, there is some extra symmetry. And this extra symmetry helps us to decompose this complex into two pieces. And that's what we want to do. And then after that, we will move over to Riemann surfaces. So let me now erase everything except this thing here. Okay. So so let's define that omega 1, 0 of U. This is called the space of 1, 0 forms over U. This is the set of all forms of the following form: F dz, where F belongs to C infinity of U, right? And what is dz? Dz, of course, we know, is by definition, is dx plus I dy. Right? So these are special types of one forms. Not every one form is of this form. So let's just say these are one form which are of this form. F is a complex value, the smooth function on U, and okay, and then omega 0, 1 of U is the set of all F dz bar, where F belongs again to C infinity of U. Well, again, dz bar is equal to dx minus I d bar.
Professor, f is a complex function.
The complex valued function.
And it's in C infinity, meaning that its real and imaginary parts are differentiable, or
Yes.
does it mean that it's holomorphic?
No. They are not holomorphic. No, they are just smooth. C infinity.
So the real and imaginary parts are infinitely time.
Yeah, even you don't even have to decompose it into real and imaginary. You can just define partial derivative with respect to x and y of any complex values function.
Okay.
You just define the usual definition. So
right.
Okay. So these are these two things. And the first thing we observe is that we note that omega 1u, every one form can be decomposed in a unique way as a sum of 1, 0 and 0, 1, 4. Okay, this is important. Omega 1, 0 of u, direct sum, omega 0, 1 of u. Okay? So this is really a direct sum. These are subspaces, complex subspaces of this complex space, and this follows from the following fact that we have dz equal to dx plus I dy, and dz bar equal to dx minus I dy. Now from here you get that dx is equal to you just add, you get half of dz plus dz bar. And if you subtract, you get dy is half of, is just half of, no, not half, 1 over, okay, so I and I is 2i, I get 1 over 2i, dz minus dz bar. Right? So once you have, then what you can do is the following. Once you have a 1 form, you can replace dx and dy by these things, and then you write everything in terms of dz and dz bar. And decomposition is unique because you can go backward, and then you have dz and dz bar in terms of this. So there are like two different bases for space of one forms at that point. Okay, then what happens to the differential? So for the differential, there's this little lemma here. Is that the Courant differential D also decomposes as del plus del bar, where this del of f is df dz and del bar f is equal to df dz bar. Now, what is df dz? So df dz I already defined. I mean, you can just say, okay, this is just simple complex derivative with respect to z, but let me also define it in an alternative way, which we can define. Okay, where d dz is 1/2 ddx minus I dy and d dz bar equal to 1/2 ddx plus I dy. So,
sorry, is it equivalent to
okay, let me write it here. D is equal to this. Yeah.
So this d over dz, is it equivalent to the definition of complex differentiation?
Complete.
Exactly the same.
It's exactly the same. Yes. You can write it that way. Yes, exactly. Okay. Okay. Now to prove this, we just substitute for d and d bar and check that this is the same. Okay, so proof of lemma. Okay, so we want to check that df. Okay, so we want to check that, for example, df, why this is equal to df plus del bar f. Well, left-hand side is df dx plus df dy, right? So what is right-hand side now? Right-hand side is, well, this partial is df dz, which I know is df dz dz plus df dz bar dz bar. So what I'm going to do now, I'm going to replace the values of dz and dz bar from these equations, write everything in terms of partial derivatives, usual partial derivatives, and then that's equal to now. Okay, so oh, this is the one I need. So this is equal to half of. I'll just write it like this: half of ddx, yes, minus plus minus idd minus iddy, and then I multiply this by. I'm supposed to multiply by dz, which is dx plus idy. And then I have to add to this half of ddx plus iddy. And then you multiply, you're going to get dx minus I dy. And of course, I'm applying this whole thing to f. But this f doesn't play a role. It's just a symbol now. Okay, if you multiply these things, and there are 4 terms that cancel and 2 terms that add to each other, you see that this is equal to left-hand side. You just multiply this thing. You see, you get ddx dx, okay, and then here, then there's a cancellation. So with this term, ddx dx, this remains. Half and half is 1. Now ddx dy, there's an I and there's another one minus I, and they cancel each other. So there's a cancellation and there's addition of 2 terms.
What about I dy times dx?
Yes, so which one? I dy
Times dx.
times dx. So there's this minus half of I dy dx here, right? And here, so you mean which one cancels with that?
Okay, never mind, sorry. Okay,
You
no,
figured out?
yeah, no, yeah.
Okay, yeah. Because I was looking for
Right.
find the answer, but you. Okay, so that's good. Okay, so I mean, this is so now we can just write the Rom complex in the following form, which is really using the power of complex variables and complex structure. So this is this crucial lemma. So the corollary is that the Rom complex is decomposed in the following way. So we just put instead of omega 0 now, I'm going to put omega 0, 0. So maybe I put it here. U. And then so I just go to omega 1, 0. U, and this is by, I go here by del. I go here by del bar. And this is omega 0, 1 U. Okay. So then I go here again by del. I come here to omega 1 U. And then here I go up by del bar. Okay. So again, so the only thing I have to define now are this term and that term, right? So omega, then these are very easy. Omega 0, 0 is just omega 0 of u. It's just a smooth complex valued functions, and omega 1 of u, okay? Omega 1 of u is really nothing but omega 2, again, complex valued of u, which I noticed that it can be written in the following form, can be written as f dz wedge dz bar, where f belongs to C infinity C of u. You see, before I wrote it as f dx wedge dy. Now I'm writing it as f dz wedge dz bar, but they are the same. If you multiply this, as I did last lecture, dz wedge dz bar, only the term that remains is dx wedge dy. And there's a factor of 2i which is absorbed by this f. So the two spaces are the same. So this is the actual way we want to think about Durand complex or differential forms over Riemann surfaces very soon, actually. But we are over U now, or just an open subset of C. Okay. Any questions? So you see the relation between this complex and this double complex. Yes.
So what's happening to the zeros at the end?
What happens
What's
to
happening to the zeros at the end?
zeros?
The zero at the end of the previous one?
Oh, yeah, if you want, you can just say this goes to 0 and this also goes. You can do that. But the question is, what is the relation between this and that in view of the decomposition that I have? This is just the total complex of this complex. The total means if you take the diagonals, direct sum the diagonals, and there's only one interesting diagonal, you get this complex. And this is something that happens on n-dimensional complex manifolds also. You can do this decomposition. In that case, then you have this double complex, which is big, and so this is the extra symmetry that exists because of complex structure. You don't have over real manifolds this extra symmetry, and this is much more deeper than what you have for the Durand complex. Much more finer invariant we'll get. Okay. Yes.
I'm not sure I understand the diagonal.
Oh yeah, this is a little bit of homological algebra, maybe to total complex. You have to know a little bit about double complexes. Just ask me after the class. This was for those who have taken homological algebra. I don't know. When was the last time this was taught here? Maybe recently. I mean, it's also, you see it in algebraic topology. So. Okay, so now what we can do, we can make some definitions. So now let me define the idea of holomorphic one-forms. So this is what actually now is kind of, maybe you were worrying about this actually. So let me define it. Holomorphic one-forms. So what is a holomorphic one-form? Well, a holomorphic one-form is something that's here, but it's in the kernel of the bar. So that's, okay, I mean, there is an unfortunate notation that's used by any books and used by many authors, but it comes a little bit into conflict with this notation, but that's okay. So I just define notation is omega u. Ooh, that's not. So what is this? So I mean, I don't put any index here. So maybe that's a distinctive feature. No index up or down, just omega u is very important object. So what is that? That's the set of all omega belonging to omega 1, 0 of u, such that del bar of omega, del bar of omega is equal to 0. Okay? So what is it now? Let's explore this a little bit. So this is the set of, so let me write it. This is the set of all. So what is, first of all, omega, which is in omega 1, 0? How does it look like? If something in omega 1, 0, there is a function times dz, right? That's what it is. So there's the system of f dz, right? Such that del bar of f dz is equal to 0. Now, what is del bar of f dz? Del bar of f dz, by our rules, this should be del bar of f dz bar wedge dz, right? So if this, because this is a basis now, if this is going to be 0, it means that this has to be 0. So del bar of f is equal to 0. So what does that mean? Del bar of f equal to 0. What was this equation?
Riemann.
Cauchy-Riemann
Riemann.
equation. Yeah. And this means that f is a holomorphic function, right? So this is Cauchy-Riemann equations for functions. And this is just, of course, means that f is holomorphic. Okay, so holomorphic one form is on U, on some open subset of C for now, is a one form, first of all, which is of the form f dz, but f has to be holomorphic. Okay, so f has to be holomorphic.
So, this Cauchy-Riemann equation that works here, is it on a open set U, right? Because if it's just only at one point, it's not holomorphic.
No, it's not one point, it's on U, all over U. It's all over U.
So all these forms are always on a open subset of CU.
These forms? Yeah, they are all on U, yeah.
Okay.
I did not talk about the point. You can do that, but then you have to define the tangent space, cotangent space, and take the sections of those. That's a longish route, which we don't want to.
Right, so we always consider them open.
All over U. I mean, that's eventually you have to do that, but that's for most of what we need is avoidable. Okay. So so now so we have that now. What I want to say now is that we want to move this to manifolds, to Riemann surfaces. Okay. So the next step is because I mean doing things over U is not enough. So now move everything to move over to Riemann surfaces now. So then what happens for any Riemann surface, we can define such a complex actually. I mean, that's not difficult now. So we want to define things like omega 0, 1 of, okay, so for any U subset of X open, U belonging U domain of coordinate chart of a holomorphic coordinate chart. Domain of a holomorphic chart, we can define this complex star. we can define a star. That's not a problem, because you're on this abstract Riemann surface, that's true. But then you just use a coordinate system to come down on Earth, from the sky, you come down on Earth, open subset of U, you take this as the Durham complex and this decomposition over that. And we insist that all these choices should be compatible with respect to pullback of transition functions as we did in the last lecture, right? And so the condition is that. So then, so the requirement is that compatibility of star in with respect to transition functions when you go from one coordinate chart to another coordinate chart. So there is something that should bother you and should worry us. Namely, is this really a well-defined concept? You see, in other words, is this decomposition really independent of choice of coordinate systems? That's something that we have to worry about. If you just have a two-dimensional surface, a smooth surface, and you declare dz and dz bar and partial derivatives just like that, you can check that this is not going to be compatible when you go from one coordinate system to another coordinate system. Something that's expressible in terms like is written as f dz. If you go to an arbitrary new coordinate system, it's not going to be of the form f dz. It's going to be of the form a dx plus b dy for general a and b. Because dz is very special. It's dx plus I dy, and dz bar is but the fact that this form is preserved is a consequence of existence of holomorphic coordinates. So let me tell you something, check something for you so that you can see what's going on. So here's an example. I think everything I want to say is in this example. So imagine you have a one form, omega is like f dz, just f is smooth. Okay. Let's change coordinates, but holomorphically, and then we'll see that the form of this guy is going to be preserved. Okay. So change coordinates. So the new coordinate is something like z equal to h of w, but h is holomorphic. Okay. So when you go to this new coordinate, then omega, which is f of z, is it becomes the following, it takes the following form, f of h of w, right? And then we have got d of h of w. What is d of h of w? What is d of h of w?
H prime dw. H prime dw.
What is h prime? But we have to be a little careful. We have to be a little careful, but because we have a different definition of d, which is equal to del plus del bar, right? So this is equal to, now what happens, so h of w, this is equal to actually, okay, so if I want to write the end result, I say this is h prime of w, dw. But the question is why? This is equal to h. You see, if you believe in this, then you're done, right? Because dw.
So how do you drop the DH down?
Huh?
You drop the DH down.
I dropped the DH. No, DHW is here. So f of h of w. Oh.
Oh.
I meant to put a question mark here. Yes. Times h prime of w. This is like chain rule. This is complex chain rule if you want. Okay. So complex chain rule. But I mean, it's not quite complex chain rule. I'm cheating a little bit here because f is not holomorphic. F is only a smooth function. H is holomorphic. So I have to provide still an argument why this is equal to that. So let's compute d of h of w. I mean, yeah. What is d of h? We had a result before, right? Or of h, right? This is what I proved in this lemma that we had, right? We had the lemma. Now, what is this? This term. Del bar of h is 0 by Cauchy-Riemann equations because h is holomorphic, right? So this is 0. So this is equal to del bar of h. Oh, sorry, del of h. But what is del of h? Del of h is d dz h, right? dz. Well, actually, it has to be dw because now I'm thinking in terms of w. So this is, I put here dw, I should put. I mean, so you see that when you go to this new coordinate, the form of the function is preserved. The form of the one form is preserved. If your one form is of the form f dz, in the new coordinate is also of the form g, some a function of w times dw, and nothing else. And that's the whole reason that this decomposition makes sense over Riemann surfaces, and that's the whole reason that we can talk about one forms and all these gadgets over Riemann surfaces in this type decompositions. So now we just so we'll work on some questions so that it becomes more palatable for you guys. So let me just take two examples. Any questions, by the way? Okay, so
Having general question, but not about like general question about forms, is that when we define forms this way with these definitions and notations, and when we also like use chain rules there, but sometimes, for example, when you integrate that and the chain rule works exactly how it should,
yeah,
why does that happen?
well, we'll see. I haven't defined integration yet, but you'll see it now. So let me now take some simple examples of this. Okay, a couple of things to know is good. So here's example one is, for example, you want to check that holomorphic one forms are closed. I mean, this is something that we have to see, and it's good to test our understanding against these simple questions. So holomorphic one forms are closed. First, so we have a one form. You remember what was the definition of closed? That's what we use in order to define the wrong cohomology. What closed meant?
D of W is 0.
D of omega.
Omega,
Yeah. Sorry,
Omega.
you're absolutely right. I have the same problem. My omega and W's are actually quite similar. So yeah, closed means the following. Means kernel of D. Okay, means belonging to kernel of D. Means D of omega equal to 0. So now, what does holomorphic mean? Is omega of the form what? F dz, right? Where F is holomorphic. That was our definition of holomorphic bound form. F holomorphic. So what is holomorphic? What F holomorphic means in terms of Cauchy-Riemann equations means that del bar of F is equal to 0, right? Or that's the definition of holomorphic, right? Okay, so you have a one form, which is of the following form, a holomorphic function times a one form dz. Now we want to show that this is in the kernel of D, but we know what D is. D is del plus del bar, right? So let's compute D of omega. So this is del plus del bar of f dz. So by linearity, this is equal to del f dz plus del bar f dz, right? And del f dz plus del bar f dz, right? Now, what is del f dz? This is d dz of f dz, base dz. Now, what is del bar f dz? Del bar f dz is df dz bar base dz, right?
But it's not 0.
What's that?
It's not 0.
Well, we see that, yeah, exactly. That's what we need. Yes. Okay. Now, both terms are 0. Both terms, but for different reasons. You see, the second term is 0 because this coefficient is 0. That's the second term is 0. The first term is 0 because of dz base dz is 0. So both terms are 0. So the sum is 0. So this is indeed in the kernel of D. So what happens is that if you take a holomorphic one form, this is automatically closed. So it means that it defines a class in cohomology. So it has topological information. Holomorphic one form. They have topological. They are not just some one forms, random one form. They carry information. Is that so? This is a typical simple calculation. It's good to understand. Any question about this? Now, let's look at another example. Of course, you can also show that. So here's example 2, maybe. I'm saying every closed one form omega belonging to omega 1, 0 of U is holomorphic. I mean, so this is if and only if a statement. So an element in omega 1, 0 is closed if and only if that form is holomorphic. So there's a one-to-one correspondence between holomorphic one form. I mean, the proof exactly is here. There's no difference. You can go backward. Okay. Question, yes.
So just, why again is the df/dz bar 0?
Oh, yes. Why df dz bar is equal to 0? I said f omega is a holomorphic one form, right? What is holomorphic one form means? Means that it is of the form f dz, where f is holomorphic function. And holomorphic function means del bar of f is equal to 0. This is Cauchy-Riemann equations.
Oh, okay, yeah.
Yeah.
Thank you.
This is a consequence of holomorphicity. Yeah. Yeah. So another example, maybe then it will completely, confirm your, I mean, would just help your understanding now. So let me give another example to get more familiar with these concepts. At first, it's a bit maybe too abstract or notationally complicated, but it's not. So this is part 3 of examples. F belonging to infinity of u is a harmonic function. If and only if del f is a no, if and only if df oh yeah, del f, which is del f del z dz is a holomorphic one form. Again, it's a simple little exercise just to help us practice a little bit of this yoga or gymnastics of this dz bar, dz bar, and this. At first, it's a bit confusing, but it will disappear. The confusion will very soon disappear. Okay, so let's recall. Do you remember what harmonic meant? Do you remember what was the definition of harmonic function?
If when you differentiate twice with respect to x, twice with respect to
Y is equal to 0. Exactly. So this basically harmonic function meant the following: d2 dx2, right, plus d2 dy2 of f is equal to 0, right? That's the definition of harmonic function from complex analysis 101, basically, or calculus, multivariable calculus. Okay, now you can write this in a very interesting way. A2 plus B2, you cannot factorize it using real variables, but you can factorize it using complex variables. How? Well, I mean, you can just write this as d dx, right, plus I d dy times d dx minus I d dy. And then there is f equal to 0, right? Do you agree? I mean, this is very simple check. You apply this twice, means that you're partial derivative second, and then this cancels, and then the cross terms actually cancel each other. Okay? Now we can write this in the following form. You remember what was this differential operator? You remember this differential operator? ddx plus I dy and ddx minus I dy?
That is Z bar and that's it.
Exactly. This one was d dz bar, partial z bar. And this one was partial z. So this is, well, of course, there was twice business going on, right? So we have to be careful. D dz. Oh, d dz bar. Yes. There's this d dz bar. And then twice d dz. Right? Because I define d dz to be half of this and d dz bar to be half of the other one. So there's two. So basically, this means over f is equal to 0, right? So what does that mean? It means that now I can interpret this in the following form. If I take d dz bar of df, I mean, okay, there's 4 times, and 4 cancels anyhow, because this 2 and 2 is 0. So d dz bar of df dz is equal to 0, right?
Is it allowed to interchange?
I can interchange even. It's not a problem because this guy is interchangeable, so the linear combination is also interchangeable. So I just interchange. This is equal to d dz bar of df. Oh no, d dz of df. df equal to df. Oh no, this is actually, I don't have to interchange it. Okay, so this implies that d is a bar of df dz which dz bar is equal to 0. I haven't done anything. I have just multiplied by this basis element. These are non-zero. So I just rewrote it in a different form. And if you think about it, this is just omega df. And this is exactly the condition for this coefficient to be a holomorphic function. So this is a holomorphic one. That's the end of the story, right? So we get this plus. Okay. So, any questions? Okay, I think it's a good time to stop now, and then we'll go and define the residue of one forms. Okay, we'll do some more examples on the residue and integration, and then the residue theorem I will call for you. If you have no questions now, you have questions? Okay, you can ask questions anyhow later. That's okay, so.